Hey physicists, going to take a look at the three problems that are part of Rotational Motion 3 Expert TA session. Right. Hey, so the first one has this duct sitting on a beam, and we're trying to look at the forces on the left and the right pillar, and the last one says, hey, what's the scale reading for both pillars? Taking a look at the force on that right pillar. Right. Hey, when we have a situation like this, the whole thing is at rest and remains at rest. So we know the sum of forces are equal to 0 and the sum of torques is equal to 0. And that's true for every point. I'm going to pick this pillar on the left to say that the sum of torques is equal to 0, because that ends up being pretty handy, because that way any force going through that pillar does not provide any torque. So if I look at the torques about that pillar on the left, then I have the duct providing a torque to the left, the mass of the beam providing a torque to the right, and then I got to figure out this is either going to have a force up or perhaps a force down, but it's going to provide a torque either to the right or to the left, so that the sum of these forces is going to be equal to 0. And now when we're looking at a torque, torque is equal to the radius at which the force is applied, cross product, remember that, but we'll assume these are at 90 degrees, okay, times the amount of force. And in this case, hey, the sum of these torques is going to be equal to 0. Hey, in this case, I'm going to call, let's see, right-hand rule rotation out of the page or clockwise as being the positive direction. Okay, hey, so I'll add up the torques. The torque from the duct would end up being, what is this going to be? The torque is at, L over 3 times the mass of the duct times gravity, because we need the force for the weight of that. Okay, minus, now I have to subtract the torque due to the beam. The beam is acting only over a distance from here to here. That would be half of the distance between the two pillars. So that's going to be L over 6 times the mass of the beam times the weight of the beam. And the last thing we end up having is our torque from the, let's see, from the pillar. So times that force on the right times L over 3. L will cancel out of all this, so if I isolate for my force on the right, I get 1/2 mass of the beam G minus mass of the duct G. For part B, you can do this similarly, except your rotation would be about the pillar on the right side. And part C, remember that our forces have to be equal to 0. So probably not surprisingly that if we were to add up the scale readings for the pillar on the left and the pillar on the right, that has to support both the beam and the duct. So you'd have the weight of the beam plus the weight of the duct. Hey, in number 2, we have a situation where we have a door hanging from 2 hinges. Remember on this one, our free body diagram is the forces that are acting on the door. So we have, of course, the weight of the door down, okay, and then the hinges support the door from falling down, but they also end up supporting it so it doesn't, let's see, at the bottom, if there was no hinge, the door would push to the left, so we have to provide a force to balance that. And at the top, if it wasn't pinned, the door would fall away from the hinge, so we need to have a force holding it against the door jamb. Hey, question B asks about the amount, and also notice direction of this force. I'm just going to be pointing to the left, so don't mess up by forgetting to put the minus sign. But again, the sum of our torques has to be equal 0, but I can pick the point about which all this happens. What I'll do is I'll pick this lower hinge. So our torques have to be equal to 0. The weight is going to be acting along this line. I can do all that fancy stuff with the sign and where it's applied, or I can just look at the line of force. Whether I apply the force right at the center of the door or along that line of force right here, it doesn't make a difference as far as the torque, because it's acting along this line. Right? And so from this, I have a certain moment arm out from this pivot point, okay, and that'll be rotating it to the right. Or we could also call that clockwise, or we could also call it right-hand rule into the paper. And so therefore this other torque on the up from our hinge has to produce a torque to the left, or counterclockwise, or right-hand rule out of the page. Okay, so looking at this tells us that our sum of torques is going to be mg times the moment arm, or the distance that line of action gets from our pivot point, which in this case is going to be h over 4, minus the force 1 in the x direction times the distance that is from our pivot point, which in this case is h over 2, has to equal 0. And do a little math, and we can figure out what that value F1 is. Hey, maybe a note, why did I ignore F1 Y and then both of the F2 forces? Remember, I'm taking this point here as my pivot point. All of these forces act through that pivot point, therefore they produce no torque. The only forces that are producing torques are the weight of the door along this action line, and then just the X component of the upper hinge, which is acting through this line. Hey, by inspection, we can solve C pretty easily, which is asking, hey, what's the amount of force here, F2X? Remember, our door is stationary and remains stationary, so the sum of forces is equal to 0. If we look at the forces in the X direction, we only have F1X and F2X, so those two have to balance. Hey, for D, we have a bag hung all the way out on the doorknob. Okay, so we still have the same condition where in B that our sum of torques has to equal 0, but in this case we have mg h over 4, and we'll call rotating clockwise the positive direction, minus F1x h over 2. But then we have the additional torque, and it's going to be a clockwise or right-hand rule into the paper, produced by mg, but notice this time it's all the way at the full width of the door, which is h over 2, and that has to equal to 0. Now we just isolate for our value for F1x. You can see that the sign will still be negative in this case. And then for E, all we do is we take that, we move it to the center of the door. So you can probably see that our moment arm, whoa, I see an error here, that's a 4. Okay, that because we're moving our force closer to our pivot point, that our moment arm becomes less. All right. Hey, so in a few moments we'll start number 3. Hey, number 3 has this beam. This beam here, in here, yeah. That is supporting a mass hung by a cable. The beam itself is held up by the tension in this wire, and it's also supported down here against a wall by a pivot point. And so if we take a look at the forces that are involved in here, we can kind of go through. We see that there is, let's see, a force of gravity on it from that big mass. So I'll put a force of gravity on the, I'm going to use B for beam. beam from the mass hanging there. Also, I guess I could have called that tension. Okay, there's a force of gravity on the beam from the mass of the beam itself. Right? Other things that are touching it now, we know there's a tension force acting that way. A force of tension acting on the beam from, I guess I'll call it the cable. And at the wall, we have a force. I'm going to break it down into its two components, just because the problem asks for that. Normally we wouldn't break it into its two components at this point. But we can see that something that the wall has to both hold it up and also push out on it, or else the beam would kind of crush into the wall. So I guess we can call those normal forces. Force normal on the beam from the wall in the x direction, and force normal on the beam from the wall in the y direction. Okay. And again, in this case, our sum of forces needs to be equal to 0, and our sum of torques needs to be equal to 0. And we can pick the point that we're doing our rotation about. I'm going to just take a quick look at A here. I won't go through every step in here, but give you enough to get started. Right? So I realized A was this free body diagram. B is the lever arm or moment arm for the weight. So let's draw that up. Hey, I realized I mislabeled this previously. It should be the force of gravity on the beam from the Earth, and the beam has a mass of m. I think I ended up putting an m somewhere in there. Right. Hey, so B asked, hey, what the lever arm for the weight of the beam? Okay, we can see that the beam is acting along this line of force. Okay, so our moment arm is really just this length here. You know, I shouldn't call it R. Hold on a moment. Okay, I'm actually going to call it L, and you'll see in a moment why I did that. Okay. This is the point at which our line of force is perpendicular, let's see, to our pivot point, which is out here. Hey, remember that a torque is R, and that's why I didn't want to use the value R. R cross product force, and we can define that as being RF sine theta. All right. And so we could say that this value L is, hold on a moment, pause. Hey, another poor choice of things. Hey, I'm going to change this theta to a different value. Right? Hey, just change it to phi. You'll see why, because theta was in the problem, right? Hey, but so phi is the angle between the two vectors, all right? So I end up having this radius vector. Notice it comes from only the midpoint of this out here. So my vector R is this one here, and then I have my force acting downward. And really, what we're looking at is, hey, what the moment arm is when this is at a 90-degree angle. How long is L? Hey, in this one we can see that the angle theta is actually this one here. So we see that this value L is equal to 1/2 L, because this radius R is only 1/2 L. And then because we're measuring the other angle, it's cosine theta. Sorry about that mess up here, but as theta gets larger and larger, the line of application of force is closer and closer to the pivot point. Okay, so you can see where if I was straight up and down, I would produce no torque because that force would travel right through the that pin. Hey, and likewise, if we're looking at that weight that's hung out at the end over here for C, you can probably see that the moment arm, or the distance that the line of force acts perpendicular to the pivot, would be the full length L cosine theta. Okay, so let's take a look at, I can scroll this down. Okay. Oh, I got to draw a new picture here. Hey, for D, what are we looking for D? D is saying, hey, what's the magnitude of the torque about A created by the tension in that cable. So we end up having that cable out over. Let's say cable is pulling this direction, T at a distance L, right? About point A. Okay, so what do we have to do? Okay, we have a radius out this way. Oh, how'd that happen? Out that way, that's our radius and our tension. So, hey, we can go back to our regular equation for torque. Hey, the torque is R cross F. Hey, in this case, we're looking at the magnitude, which will be RF sine of the angle between the two. In this case, that's going to be theta plus, what is it in this one? Plus phi. Our force in this case is T, is the tension, and the radius is our length L. So it looks like our torque about A from the cable, at least the magnitude of that, will be, we got tension times L times the sine of those two angles together. The closer they get to 90 degrees, the more efficient it is. And then E, let's take a look at E. E is asking, hey, what the magnitude of the torque is. So how much is our torque? Hey, we know that the sum of torques is going to be equal to 0. We know that TL sine phi plus, theta plus phi, okay, that's twisting it right-hand rule out of the paper or counterclockwise. And then we have two torques that are twisting it the other way. The weight of the beam is trying to rotate it clockwise, and then that mass that's hanging off the other end. So if I call that one the positive direction, I'll call the other one the negative direction. So what do we end up having? That was M of the beam, G, and then the moment arm was L over 2 cosine theta, and then we had that big mass hanging off the end, which was, I'll put it down here, also run off the edge of the paper, MGL cosine theta. Hey, so everything, let's see, this all adds up to 0, right? So we can move a few things around, isolate for T, everything else is given, we can solve for T. Hey, so what's F asking here? Hey, what's the horizontal force S of X at the wall at A? Hey, we know that the sum of forces equals 0, which also means the sum of forces in the X direction have to be equal to 0. So I look at this thing, the only other thing that provides a force in the X direction is this T. So whatever the X component of T is has to be balanced by the that force, I guess we're calling it S. S of X has to be equal to and opposite in sign to the tension forces X component. Hey, and the last one, I know this is getting kind of long, sorry about this, but if you have more questions, stop in and see me. Hey, so the last one is, what's the Y component? I know that the sum of Y components is equal to 0. Let's think about what has what this has to support. We know that there's force of gravity down from the beam, so I'll say F of G on the beam from the Earth. We know that there's a force of gravity on that mass from the Earth is also acting down. Hey, this tension force up here has a Y component, so that's pushing up. That T of Y is acting upward, and we add all of those plus, I guess I should call it S, and we call it, sorry, S of Y. When we add that all up, it has to be equal to 0. So right now you should know what that is, you can figure out what that is, so you can figure out what that Y component of S is. All right, got questions? Stop it and see me.